Following our agenda, we have a couple of presentations from the two pilot projects. Let's start with EUPILOT, the presenter being the coordinator of the project, Carlos Puchol, from the side of Barcelona Supercomputing Center. Carlos has had a lot of industry experience and has studied in the US and worked for several companies in that field. And he has been managing this project that takes a system level view, not just chips. And I think he has a lot of war stories to share if he wants, and also like an optimistic perspective that we will get such things under the European funding. Carlos, I appreciate that you took the time to be with us today. Please go ahead with your presentation.
Thank you. Thank you, Manolis.
Okay.
Okay. I think for now. All right. Thank you, Manolis. I'm here to talk about EUPILOT project, which is, as many of you know, one of the two parallel projects that are working in conjunction with EPI to take technology from EPI and experiences from EPI, and then take them to the next level and then produce demonstrators for it. This is an overview of the partners in the project. Many of you know are either in some of them or here. And the project is about 30 million in budget. And is it not sharing? Okay. And here's an overview of the 19 partners in the project. Let's get to the objectives of the project. The objectives really, the broad objective is to demonstrate European pre-exascale accelerator platform. And how do we do that? First, we have to design and build that platform. The idea is to maximize the use of European technology to the extent that is possible to do as much as that as possible. Stimulate collaboration between industry, research centers, as well as academia. Doing that as well is very important to leverage all the things that we have right now happening, which are very exciting. That are open technologies like RISC V and Linux and all the tool chains and tools that are easily available. And then, of course, part of it is do it in a way that is, we create an accelerator that is energy efficient, so that we do it in a sustainable and efficient manner. The overall goal is to strengthen the European digital autonomy, as well as the supply chain for HPC and AI. So as you have heard earlier today from both Filippo as well as Etienne, EUPILOT leverages from the efforts on the accelerator side of the project, of the EPI project. And then EUPILOT, in collaboration with COEs, as well as the project, the EUPEX project, which is essentially the symmetric project with respect to the CPU track of EPI. The idea is that with this and these learnings, we basically, the project is basically a stepping stone towards bigger and better things. In this case, is kind of a precursor, if you will, to the DARE project that many of you know. So we have a video that it kind of like Manolis very well said. It's a project not just about chips, but there's software, there's boards, there's deployments, and all that.
Can you imagine a future where the entire semiconductor value chain is provided by European sources? The European Pilot project is a key project towards realizing this goal. World-class competitiveness, leadership, and self-reliance in industry and science are now more important than ever in Europe. Bringing a new level of high-performance computing, data analytics, and maximizing the use of European technology, EUPILOT makes use of open source and open standards to create an integrated software and hardware system. From microchip designs to the systems incorporating them to deployment in data centers, EUPILOT pushes the envelope in high performance and energy efficiency. With a streamlined software stack, EUPILOT systems are being designed to accelerate computationally intensive applications in the fields of molecular and climate modeling, genomics, biomechanics, geophysics, and many other domains. EUPILOT is creating two complementary RISC V accelerator chips designed, implemented, and deployed in Europe. One for vector-driven tasks like scientific computing, called VEC, and another for data analytics, AI, and machine learning applications, called MLS. Each VEC accelerator contains an array of compute tiles, and each tile contains a CPU and a vector processing unit. The MLS accelerator contains clusters of a larger number of small yet efficient cores specialized on computations most frequently used in data analytics, machine learning, and AI. These chips, coupled with memory chips, form accelerator modules, and multiple modules are hosted on a baseboard within a chassis to form an accelerator system. Each accelerator system is then paired with a host server and is immersed into a liquid cooling tank which can hold up to a dozen hosts and accelerators. Gone are the days of server racks taking up an inordinate amount of power. Now, multiple liquid-cooled tanks can be deployed in a data center for a large integration of compute capacity and density at unparalleled levels of power and cooling efficiency. The European Pilot, contributing to a sustainable exascale supply ecosystem in Europe and ensuring European digital autonomy in this field.
Great. All right. Thank you. So that kind of gives a very compact view of the project, from leveraging the technologies from existing projects to all the way to deployment in data centers. So looking at work streams in the project, we have the hardware stream that has taken the technology that has been worked on before, that you've heard earlier from Filippo and Etienne. Takes this tape outs of the accelerators in 22 nanometers and then deploys them in both 12 nanometers and also 7 nanometers. We also taped out last year a test chip to do verification of the technology for the VEC chip. In addition, we have, of course, software to run on these platforms, as well as the tool chains, and a lot of the work is also up the stack to be able to run applications, and so you need libraries and that sort of thing. In terms of systems, we do have a big involvement here, both at the system level in terms of software, as well as system, because some of the boards are designed right here at Forth. The idea is that, as I go into more detail in a moment, the idea is that these systems will eventually be deployed into liquid immersion tanks, which what they do is basically they enable higher workloads, and then they reduce the environmental impact that we have. Ultimately, two goals that we have are to demonstrate EUPILOT working system, a demonstrator in an environment, a data center, in this case at the Mare Nostrum data center environment, And then the ideal situation is that it also becomes a stepping stone towards, like I mentioned, as an SDV for upcoming projects. So let me just recap, because there's many pieces. So we have, I can move the mouse and it can be seen, maybe. No, that's okay. That's okay. There's no big deal. Oh, to the laser.
Oh, you can move.
Okay, I can move. So basically, we have a host server, which could be a regular x86 or an ARM server, or the goal is to be paired with a UPEX system with RIA inside, and then that gets paired with an accelerator system that has multiple chips on multiple modules, and eventually those things get deployed onto liquid immersion tanks. So now we're going to look into what's in one of these boards. The chip is inside, underneath one of these, heat sinks, which in the case of the immersion tanks may not be that big. So this is basically what we call an EUPILOT accelerator module. And so it's a module like this, which is the same form factor that AMD and Intel and others are starting to use for AI deployments. NVIDIA is also a similar form factor, but it's proprietary. It's not OCP based. And so the idea is that this module contains the EUPILOT chip, as well as memory, a number of chip-to-chip interconnects, and one CXL PCIe Gen 5 interconnect to talk to host. Looking a little bit into where does this go? So this blue box now with two connectors for interconnecting all these IOs. Then they go into this. So each one of those with one chip and memory and so forth is each one of these boxes over here. And then they all go into a so-called universal baseboard, or a UBB, which is a board that has a network interconnecting them, a coherent network interconnecting them. In this case, is one of the partners, Xtol, that is providing that, and that was also mentioned by Filippo in the talk. So we kind of leverage the technology, and then we also take it one extra level to 32 gigabits per second. This network over here, then it really interconnects only the chips, but each one of them, they also talk to a host interface board, which is essentially a switch that talks to the host system. So that's a typical architecture that we've seen. And in terms of software, I'll talk very briefly. The VEC software architecture looks the MLS software architecture is quite a bit different, but the VEC software architecture looks like a traditional HPC system with an MPI cluster manager, and then each one of these chips potentially interconnecting, sharing memory between them, are cluster workers, and then they look like Ethernet devices or PCIe, just like a traditional setup. Talking a little bit more about the software stack, we have in red, the red boxes are boxes targeted towards HPC. The green boxes are targeted towards AI, and so you have the MLS accelerator here and the VEC accelerator here. And so you have the typical stack with some of the things, like some of the compilers and drivers and so forth, are going to be shared to some extent. And so you can see these are the applications that are targeted. The project itself doesn't really target a huge amount of applications, which is, we really focus on some of the top applications like GROMACS and EC Earth on the HPC side, as well as AI applications like video processing and BERT on the AI side. And then, of course, you need all the things, all the libraries and whatnot for those to work. Now, so we have a little bit of an announcement. Some people who are in the project probably have heard already. So about 2 weeks and a half ago, we taped out both chips, both MLS and VEC. So over this was a very busy summer for the team. And actually, I have a QR at the end of the presentation, and I believe actually the team has actually posted an announcement on the website and LinkedIn and all the social media stuff. So go there and click on the like and all that. So this is basically the timeline at the moment. We have taped this out just weeks ago. We expect to receive them Q1, maybe Q2 for VEC, maybe a little bit earlier for MLS. And the VEC chip will be mounted on these modules that I described before, the EAM modules. And then the modules, after being up and all of that, they will put together on these UBBs, which are rack-sized devices with 8 of these that you may have seen, similar to NVIDIA and Intel and whatnot, and AMD. And then that's what will be deployed. But of course, we're here, so it's still a lot of work to go. And so one of the things that Manolis kind of said, well, maybe you can talk a little bit about experiences and perspectives. And so the first kind of perspective is that developing hardware is a little bit like a horror movie. Something bad probably is going to happen. It's going to happen maybe towards the end of the movie, and you don't know what to do. And so that's kind of like with the teams that we have, which are, it's not a commercial product, they're relatively small teams. So this is kind of a little bit the feeling that it's you don't know when it's going to happen, but it may happen. And in fact, we had some delays because unexpected things happen, on the way. And then conversely, on the other hand, the software guys, they have to stay long hours at the end of the project, and designing the boards and respinning the boards and bringing up the systems and so forth. So this is basically a little bit of the current situation at the moment. It's very, very we are now at a very a moment where we have a lot of pressure. But if you take a look, long look, the teams, largely similar teams, like Filippo was saying, some of the same partners, we have taped out once a year. And so that's actually not that bad when you look at it that way. And so we had one tape out, another tape out. This is a test chip. And then this year, actually, we had 2 major tape outs. And so that's if you look at from the hardware point of view, that's actually quite good. Did I touch? Okay, here we go. So now going forward, we really do have to spend times on doing the demonstrations and the software and deployments and so forth. A quick update on the die for VEC. It's about 58-ish, 59-ish, somewhere in there, millimeters square. It has 8 64-bit cache coherency RISC V cores of the ones that were just described in the previous talk by Semidynamics at Trevido. Then each one of them has a RISC V VPU attached. Then there are 4 LPDDR4 controllers and PHYs running at 2.13 gigahertz. Then there's also 5 interfaces. In the picture there's 6, but at the last minute, one of these things that happened with the in hardware, we had to take one of the interfaces out due to pressures and for area, budget, and time. So the next box over here is the CXL PCIe PHY interface running at 32 gigabits per second. Actually, is the same PHY for a lot of the devices. And then there's also a 32-bit RISC V chip, which is the I/O controller for the entire chip. So all in all, we have 4 RISC V 64 cores, 1 RISC V 32 core down here, and each one of the controller, each one of the PHYs for the LPDDR has also a tiny RISC V core to do the intelligence on that side. On the MLS chip, we have these dimensions. It's on 7 nanometers. So physically is 20, so it's roughly half in area. So it's about 20 square millimeters. It has 16 clusters. Right here, you can see 16 clusters. Each one of them has 9 RISC V cores. And there's basically 10 megabytes of on-chip memory. Now, this was an opportunity, and it also has a stencil cluster, one of the accelerators that Filippo mentioned in his talk. So the clusters were basically put together in an effort between Fraunhofer and ETH in Zurich. What did I want to mention about this? Anyway, in terms of area, in terms of area, we were really actually limited by budget. We couldn't really exceed the budget that we had, so we really had to reduce the number of cores that allowed us to pay, for the chip without going over the budget. That's as much as they could fit in that area. Of course, being 7 nanometers, you could do more than 12. This is a little bit of what we expect. Now, MLS was developed initially. The goal was actually developed in Global Foundries 12 nanometers as well, and have the exact same I/O, so they would be pin compatible, and we would be able to actually run them both in modules and so forth. However, there was an opportunity after delays and whatnot. There was an opportunity to get MLS fabricated through the academic program at TSMC in 7 nanometers. And so we believe that's probably one of the most advanced nodes, out there in Europe, at least. And so this is roughly the expectations that we have per chip, and this is per system, meaning 8 modules, each module with a chip per system. And MLS will not have the same I/O. So they opted to have, instead of many more clusters and cores, they opted to have a lot of memory so that they can actually run the benchmarks within that memory, and then essentially use a bunch of wires interface to load data and then unload data, because they don't have with the time that they had, they didn't have the resources as well to get a PCIe controller or things like that. Now, one quick update in terms of what we have going on, and so now we're gearing into another phase of the project. We first have to, after they get manufactured, we have to package the chips, which is also going to take a few months. The EAM, the EUPILOT module board, EUPILOT accelerator module, with VEC and the LPDDR chips is actually being developed right here. I believe if it's not in this building, it's on the other building at Exapsys. And the what we call the ECB is the EUPILOT carrier board, or EPI carrier board. It's a PCIe form factor carrier board for bring up and for debug. So it's going to be a PCIe type board, like a GPU, where the module will be connected on. That's done in collaboration with EPI and E4 as part of these collaboration projects. There's also one debug and test baseboard that is being done at 2CRSI, where it's going to be similar to the ECB, except it's not going to be PCI form factor, and it's going to have much more test points and whatnot for the electrical verification. In addition, there's development of a UBB. This is basically either two groups of 4 or one of 8. Containing 8 modules, so it's a very large, board, and having also a host interface, so that this is the one that I mentioned that was in green in the prior diagrams. In addition to that, 2CRSI is also putting together what we call an EAS, an EUPILOT accelerator system. So one system with the UBB, with all the modules, power supply, host interface, and all the right things to be able to connect to a host. They're also designing some hosts that we are going to put together to interface, debug and manage the systems. Of course, for MLS, they will have a daughter board on which the system is going to be, the chip is going to be put on. And then this daughter board will connect with an FPGA. And then they'll have all the FPGA management of the memory in and out and all that. There's also a small development daughter board for EAM module that Exapsys is developing to help avoid having costly respins of the EAM board. So essentially, a smaller board that is going to allow them to debug the non-VEC chip and non-memory part of that board, so that we avoid any issues. And then, of course, now, literally this morning, there were meetings in Barcelona as to how the deployment of the air-cooled solutions and demonstrations with EUPEX, as well as the immersion cooling solutions are going to be. So in the end, just wrapping up, the ultimate targets are: 1, deployment on liquid immersion tanks, and then demonstrating not just in data center, but also demonstrating with the sister project that our systems can work together. And that's all. Make sure you go there, and in the EUPILOT webpage, you can see latest news. You will be able to see the release and the notes and whatnot. So it's eupilot.eu. Thank you.
Questions for our speaker?
Hello, thank you. Thank you, really. Immersive cooling is a choice or a necessity in your case?
It's not a necessity as of yet. It was basically the part of the goal was to do a demonstrator that was also energy efficient. And so the thought is that what's next in the data center world, it seems to be immersion. And so you see more and more and more. I mean, over the years, if you've gone to ISC or supercomputing, you see more and more and more immersion, because it really, I think they call it PoE ratio, PUE, sorry, P, power over Ethernet. I'm not too used to that. So the PUE ratio is much better for those systems. And it has other issues where you have to lift them, debugging and whatnot, and the physical part of it. But then again, they don't have moving parts. They don't have fans or active fans. Typically, they usually have circulation of the liquid and so forth. So it wasn't really a necessity. It was also an opportunity. That we have one of the leaders in the world, really, for immersion in Barcelona. It's called Summer. And so they're a partner in the project. And they're also developing their next generation, what they call pod, within part of the project. So this type of funding of these projects kind of helps technology in Europe to be advanced towards the leading edge.
Further questions from the room or from the remote attendees?
Thank you for the presentation. Follow-up question about the liquid rack. Doesn't that bring too much tons per square meter on the ground? You need, solid foundations for that if you have a large cluster, I believe. Do you have some studies about that, or answers or comments?
Sorry, I didn't quite get the question.
If you have a full rack full
Yes.
of liquid cooling, it's heavy, and you
Yeah.
need solid foundations for that. Is that practical with large scale systems, or?
Right. So I don't think I can answer that one because, to be honest, I don't know the ins and outs of those details. Power concerns are one issue, and that's a big deal. I know that we literally, like I said, this morning there was a meeting at the BSC to plan for what kind of modifications they need to do to the data center to host this thing. And if you think a number of years ahead, first of all, these systems, they have a huge amount of spinning things in them. They keep on failing. You have to replace them. They make a huge amount of noise, and they also burn power. And so generally, that's kind of where we're going. So this is one step into getting knowing in practice, what do we have to do in a data center to use the systems in practice? So there's a number of liquid, it has an inverter on attached to the, so if you look at in the presentation, there was here, so it has an inverter system here, and so you have liquids, coming in and out, and this basically, it's what's cooling the entire thing, and the liquid, it's the oil itself that it's used, it's not really going in and out, right? And so there's actually quite a bit. If you go to ISC next time or whatever, you will find there's one-phase liquids, two-phase liquids. There's, just a huge amount of, condensation issues. I mean, just a lot of things going on in that world. So I think the idea is to, as we aim to have digital autonomy, this is one thing that we're going to have to, eventually tackle. And it looks like that's the future. And so that's basically what we're doing. But I couldn't answer the question in precise detail.
Thank you.
Right. Any other question from the room or from the remote attendees? If not, let's thank our speaker.
Thank you.